so page 89, finishing off section 2.3. Remember that these are our practical limit laws. These are the things that give us definitive algebraic ways of figuring out our limits as opposed to having to guess them. So on the top of 89, they remind us of something that we already know, that the limit from the left must equal the limit from the right if your limit is going to exist. And on page 89, starting with example 7, we want to analyze piecewise defined functions. When we left off yesterday, we said you can never assume a piecewise defined function is going to be well behaved, even if it's made up of things that are well behaved, like polynomials or rational functions. A piecewise defined still has to be checked from the left and from the right. And so when we look at example number 7, they ask us to show that the limit as x approaches 0 of the absolute value of x is equal to 0. So they've already told me what the answer is, but basically they're asking me to prove this or to justify my answer. So when we're looking at the limit as x approaches 0, we're going to have to look at it from the left-hand side and from the right-hand side. So let's redefine that absolute value as a piecewise. We've done that previously. That was also on a previous test, so we're good with that. But remember that you have to think about if what's inside your absolute value is greater than or equal to 0, and if what's inside your absolute value is less than 0. So if what's inside our absolute value x is greater than or equal to 0, we'll get exactly what we started with. But what if what's inside our absolute value x is less than 0, then we're going to get the opposite of what we started with, negative x. So when I'm approaching 0 from the right-hand side, which of those pieces am I using? The top piece or the bottom piece? The top piece, right. So as I'm approaching 0 from the right, those are all values that are greater than or equal to 0. So I would use that top piece, I would use x. So now I have the limit of a polynomial. That's well behaved, continuous. I can just use direct substitution. So I'll put 0 in for x. The limit from the right is going to be 0. All right, when I do the limit from the left-hand side, which piece am I using? Top piece or bottom piece? Bottom, because those would all be values less than 0. Negative 0.1, negative 0.01, negative 0.001 type of thing if we're thinking of a table. So again, that's a polynomial. So it's going to be well-behaved or continuous. I can just use direct substitution. So if the limit from the right was 0 and the limit from the left is 0, then what's the limit of this overall function going to be? 0. And so I've proven that that limit was 0. And if I think about the graph for absolute value, remember absolute value is kind of that V-shaped graph, and so from the left-hand side and from the right side, all values are converging on one particular y value, and that's a y value of 0, so that makes sense as well. All right, look at another one, example 8. It says, prove that the limit as x approaches 0 of the absolute value of x over x does not exist. So again, they went ahead and gave me the answer right up front, but I've got to prove it or justify that answer. All right, so again, I'm going to need to look at it from the left-hand side and from the right-hand side, so I'm going to need to redefine this absolute value as a piecewise. So let's think about if what's inside the absolute value, x, is greater than or equal to 0. So if what's inside the absolute value is greater than or equal to 0, I get exactly what I started with, right? So I would get x. However, notice that I can't actually be equal to 0 in this function because that would give me 0 in the denominator. So typically we would say if what's inside the absolute value x is greater than or equal to 0, that's why we're going to leave the equal to off. So absolute value of x would just be x. All right, if what's inside the absolute value is less than 0, so x is less than 0, then we would get the exact opposite of what we started with. We would get negative x. And again, not equal to 0 anywhere because of that 0 in the denominator. All right, so if we're approaching this from the right-hand side, which piece am I using, top or bottom? The x over x, right. Is that well behaved? If I plug 0 in, what do I get? 0. Undefined, right, 0 in the denominator. So it's not well behaved. So I'm going to go back to what we learned yesterday. If it's not well behaved, then I'm going to try and do some type of algebraic simplification or altering it somehow algebraically to create something that is well behaved. So what could I do with this? Yeah, I could just reduce or cancel x over x to be 1. I haven't taken my limit yet. All I did was just simplify x over x to 1. So notice we're still using that limit notation. So what is the limit of a constant from our limit laws yesterday? That constant, right. So the limit of 1 would be 1. All right, let's look at it from the left-hand side. From the left-hand side, which piece am I using? The bottom one, right. Negative x over x. Not well behaved. Can't use direct substitution. So what could I do? Cancel it out, right. Simplify it down to negative 1. Now I've got the limit of a constant, and I can do that with my limit law. That limit is going to be that constant. And again, I keep writing that limit notation until I actually take the limit or apply the limit law. So if the limit from the right was positive 1 and the limit from the left is negative 1, then what's my limit? Does not exist. And what's the reason for that? The limit from the left doesn't equal the limit from the right. So if you're trying to justify that, here's a succinct way of writing that justification. Instead of literally having to write out a sentence, the limit from the left didn't equal the limit from the right, so therefore the limit didn't exist, I basically can just state the limit from the left doesn't equal the limit from the right. Now at some point I would have needed to show those two limits, but because I've already done that, I don't have to show them again. So for the AP exam, they would be looking for you to show the left and the right hand limits. They'll literally take off a point if you state them but you don't show them. So you need to show the left and the right-handed limits where you took those, and then you could just state the limit from the left doesn't equal the limit from the right with that notation. That would be your justification. Okay? So when they say prove it or justify it or whatever, as they did in example 8 here, that's exactly what we need. So as we're looking forward to that in-class bonus on old AP problems that you're doing to gain bonus points on your test, if you have a problem where it says justify your answer, that's the type of thing that we're looking for. Okay? All right, look at example 9. Here's another piecewise defined function. So we've got f of x is equal to the radical when x is greater than 4, and it's equal to the polynomial when x is less than 4. So I'm going to have to look at the limit from the left and from the right. So if I look at the limit from the right-hand side, which piece am I using, the radical or the polynomial? The radical, all right? Oh, sorry, I just was going to show you that graph back here for this guy as well, that again, at 0, you can see everything's not converging on one value. Part of your graph's converging on positive 1, part converging on negative 1. Okay, so yeah, as you told me, use the radical. Now, we have a law on page 86, number 10, said that you can use direct substitution and you can plug in for a radical as long as the value when you plug it in under the radical is greater than 0. When I use direct substitution here and I plug in 4, I get the square root of 0, and flashing lights should start going off. Because the only time I get to use that direct substitution is when what's underneath the radical is greater than 0, not greater than or equal to 0. And this was our reasoning for that. Our reasoning for that was we know what this graph would look like. That's the radical function with a horizontal shift of positive 4, so it would just square root function with a shift of 4. It would look like this. So we had said the problem is always going to be from the right-hand side, you would be able to find the limit, unless maybe it had been reflected or something like that, and it was coming in from the left-hand side. But bottom line, from one hand side, you're going to be able to find the limit, but from the other side, this function isn't even going to exist. So if they ask me to find the limit from the right, sure, I'd be able to do this. But if they ask me to find the limit from the left, or if they ask me to find the overall limit for that function at 4, it wouldn't exist, right? And so that was our warning. That was our flashing light that we had to watch out for. So what we just said was this is okay from the right, but it's not okay from the left, or therefore it's not okay coming from both sides for the overall limit, right? What did they ask me on this problem? They asked me to evaluate the limit from the right. That's okay. From the right it was okay, from the left or overall it was not. So that's why I'm able to go ahead and say, yeah, the limit from the right hand side is 0 without it being an exception of that rule. All right, from the left hand side, am I using that radical or am I using the polynomial? Polynomial, good thing, because we just said on the radical it doesn't exist, right? So they give me the polynomial. So basically what's happening here is they understand that this function only exists from the right hand side, that the problem is over here on the left, so they have redefined this function from the left hand side for me. So we'll see whether that fixed the problem and made it where I was able to find a limit or not. All right, so if we look at this from the left hand side, that's a polynomial, that's well behaved, so I can use direct substitution and I'll get 0. So if the limit from the right was 0 and the limit from the left was 0, what's the overall limit? 0, even though when we looked at this originally, we knew there was going to be a problem from the left. What they did was they redefined that function from the left by using that line. And so we can look at that and say, okay, from the right-hand side and from the left-hand side, both pieces of that function are converging on one y value. The y value that they're converging on is 0. The function isn't even defined at 0. But the function is not defined at 4, but I'm still able to find that limit. I don't care what's going on at the point. I only care what's going on as I approach it from the left and from the right. All right, example 10. For example 10, they give us something that we saw last year in pre-cal. It was called the greatest integer function. And the greatest integer function is denoted by an x with 2 sets of brackets around it. You can see it there in your textbook on page 90. The greatest integer function means the largest integer that is less than or equal to your number, x, that's inside that double set of brackets. What's an integer? Whole number, right. What kind of whole number? Positive, negative, both, what? Both. Positive or negative whole number is an integer. So basically they're saying, what's the positive or negative whole number that's less than or equal to your number? So we could go through and say, okay, what's the whole number that's less than or equal to 4? What's the whole number that's less than or equal to 4.5? 4. We got to be careful because we want to round that, right? So basically 4 point anything. 4, 4.1, 4.8, 4.99999, any one of those values is going to go back to 4, right? All right, so what about 3.5? It's going to go back to 3. What about negative 3.5? Negative 4, right. We have a tendency to want to say negative 3 on that one. But if you think about it, the whole number that's less than or equal to negative 3.5, negative 3 is bigger than it. I'd have to go to negative 4, right? So here's what the graph of that looks like. Basically, we're saying as we had any value in between 1 and 2, so 1, 1.5, 1.9, 1.999, all of those values are going to go back to 1. And as soon as you get to 2, then you're going to jump up to 2, and all the values from 2 to 2.9999 are all going to go back to 2, and then you jump up to 3, and so on. So it basically just looks like a series of little stair steps. We call that a step function then. You can also see it's a piecewise defined function. So we could also graph that on our calculator. Grab your graphing calculator if you would. So the way that I graph that on my calculator is I'm going to go to y equals, and I'm going to go to math and go over 1 to number or numeric, and then it's right down here number 5. So if I go down to number 5, that's my greatest integer function. That's what that represents. And then whatever was inside those double sets of braces or brackets, that's what I would put in here. So we just had an x, so I'll put my x in here. And if I graph it, there's that same little drawing that they had in our textbook that we were just talking about, right? And you also could ask it to find values for you or look at a table of values. So like if I gave it that one we had just a second ago, negative 3.5. Just kidding. choose value and ask it for negative 3.5, then it will give me that negative 4 that we had come up with just a moment ago as well. Okay, so that's how you can view that on your calculator. So they asked me to find the limit as x approaches 3. Because this is a piecewise defined function, I'm going to need to check it from the left and from the right. Not going to be able to do direct substitution no matter what type of equation I have. So if I'm looking at 3 from the right, that's like 3.1, 3.01, 3.001. What are all those values going to? 3. If I'm looking at 3 from the left, that's like 2.9, 2.99, 2.999. What are all those values going to? 2. So what would the limit as x approaches 3 be? It does not exist, right, because the limit from the left doesn't equal the limit from the right. What if they had asked me to find the limit at 2.5? Does the limit at 2.5 exist? Yeah, because if you're doing 2.4, 2.49, 2.4999, those are all going to 2. And if you're doing 2.51, 2.501, 2.5001, those are all going to 2. So you'd have no problem with any point on that line. Where are the problems? At the whole numbers, at the integers, right? So basically for this function, I'm going to be able to find the limit anywhere except for at the integers. It's not, the limit's not going to exist at any of those integers because that's where my steps are. All right, on page 90, they give us a couple of theorems just below example 10. The first one says that if f of x is less than or equal to g of x for x is near a, except possibly at a, because I don't care what's going on at the point, just as I approach the point, and the limits of f and g both exist, then the limit of f of x as x approaches a will be less than or equal to the limit of g of x as x approaches a. And here's what they're saying. If you have a function, like just for example, this green graph here. If this were f of x and this were g of x, because f of x is above g of x, all those y values in the green function are larger than all of the y values in the blue function, then because limit is based on looking at what's going on with the y value, if you found the limit at any point on that green graph, it would be larger than the limit at any point on the blue graph, right? That's all they're saying. So if you have one function that's larger than another or that's above another on the y-axis, then the limit of the higher function would be larger than the limit of the lower function as well, right? Then they give me the squeeze theorem. And the squeeze theorem says if you have 3 functions that you're comparing, f of x, g of x, and h of x. And you'll notice that they said f of x, which in our case is going to be our green function, f of x is larger than g of x, which will be our red function, is larger than h of x, which will be our blue function. Okay? So basically g of x is kind of squeezed in between the f of x and the h of x. So it says if that's your layout, if you've got the green function is above the red function is above the blue function, when x is near a except possibly at a, if the limit of the top function f of x is equal to a particular number, say 0, and the limit of the bottom function at that same point has the same limit, let's say 0, then the function in between would have to have the same limit at that point. That's what my squeeze theorem says. So they give me this as an example. They ask me to show that the limit as x approaches 0 of x squared sine 1 over x is equal to 0. Now, if I do direct substitution on that, I'm going to get 0 in the denominator. So it's not well behaved. And at this stage, I'd have a really hard time evaluating that limit. If I make a table of values, you can see I've got craziness going on right there in the center. It'd be kind of hard for me to figure out what was going on and what that limit was doing. So I can use the squeeze theorem to help me with that. And here's what the squeeze theorem would do. I could go through and I could say, okay, if I know the limit as x approaches 0 of this top function, x squared. Of course, the limit as x approaches 0 of x squared is 0. It's polynomial. It's well behaved. And if I know the limit of this bottom function, y is equal to a negative x squared at 0, that's polynomial. It's well behaved. So if this limit at this point right here is 0, and this limit at this point right here is 0, by the squeeze theorem, since the red function is in between the blue and the green, its limit at that point has to be 0 as well. So it would give me a way to evaluate a limit that I might not have otherwise. Now, when we see this type of problem on our homework, they do tell me what the top function is and what the bottom function is. It's not like I'm having to make those up out of the clear blue sky, so that I'll be able to evaluate the limit of the top and the bottom functions and show that they're the same, and then say, okay, then by the squeeze theorem, that middle function at that point, the limit would have to be the same as well. All right, so here is our homework for tonight on pages 92 and 93. We're doing 37 through 47 odd, 46, challenge 31.